Good. Then hello, everybody. Welcome to our next lecture. This time it's about safety in reinforcement learning, specifically for control problems. And this is my part this time. And next week we will also giving a lecture on how to use shielding to correct policies for perceived safety. So how can we use humans in the loop to improve our reinforcement learning system? But today I want to give you the initial theory to understand how can we ensure the safety from continuous action, continuous state spaces. Last times, Alexia was talking about using temporal logic, also in discrete systems, but also already showing you with STL, how you can use continuous time and continuous time signals to ensure certain properties or specifications that you have. So for RL and the safe control, it's, as we talked about already in Hang's presentation, reinforcement learning is really, really good to control complex real robotic systems, from manipulators to drones to a lot of things. However, these dynamical systems pose various challenges. We need more complex learning techniques in order to learn a policy. We need to have much better reward systems, more reward engineering, or other prior knowledge that we integrate into the reinforcement learning system to solve the problem. But one big problem for this kind of system is the safety part. So for instance, if we control a drone and we need to learn either offline in a simulator or even more important online when we want to learn with the real system, will the drone, for instance, hit a wall if you try to train flying around obstacles and so on? So maybe you have seen, for instance, these recent drone videos from ETH or some other stuff, how they fly so quickly. If we use reinforcement learning here, how can we ensure that the drone will not hit the wall? If we use reinforcement learning, for instance, for an autonomous vehicle, can we look at or determine if the AV will be able to reach its goal? So that could also be framed as desired behavior that the autonomous vehicle wants to have. So can we ensure that the autonomous vehicle is safe, but also performing desired behavior by reaching the goal region? So can we also steer the exploration phase during learning and reinforcement learning? Or last thing, if we have a human involved in our system, for instance, a human working with a mobile manipulator, and we learn reinforcement learning we use reinforcement for learning a policy, can the human, for instance, reach the robot while the robot manipulator is performing a task? So how can we first detect that if a certain action or policy will lead to it, or how can we avoid it? And today's lecture is about applying the technique of shielding that Alexia introduced in the last two lectures to continuous domains, which means we have continuous state spaces, continuous action spaces. And particularly, I want to focus on two questions today. The first one is, how can we determine if an action of the system leads to unsafe situations? Since in every step of our reinforcement learning setup, the policy is determining the next action, how can we determine if this action is safe or not? So for instance, of question C that we have here, can the human reach the robot given the current action? The second question is, in case there is an unsafe action, what do we do? Do we just don't execute it? This will work if the robot is stationary, for instance, we just don't move the robot arm anymore. Or if the robot arm is moving, or let's say the drone, and the next action might be unsafe, how can we choose another action that is safe so that we always have an alternative kind of safe backup plan that we can execute at any given moment in time? And these two questions will lead us through the whole lecture today. So given these questions, I want to talk with you today how we can design a safety filter that sits in between our reinforcement learning agent system and the real system that or the environment that we apply the action to. So our reinforcement learning agent, to speak in control kind of terms, will want to execute a desired control input U given our state. And the safety filter should check question one, is U desired leading to any unsafe situation? If not, we can just execute it because it's a safe action or safe control input. Or the second point, the second question, if the safety filter detects that this desired control input is unsafe, how can we change and modify this desired control input so that it is an actual control input that we can execute in our system? And this is what we will talk about today first how we detect if your desired is safe, or if it's unsafe, how we can change it to a different control input so we can apply it to our system or environment so that nothing happens according to our safety specification. And I hope after today's session, you will be able to first explain and define safety problems in control applications, that you will understand the differences between various control techniques that we use today. For instance, one technique that we will use is reinforcement, is reachability analysis. Then we will talk about the basic algorithms for reachability analysis and control invariance. I want you to be able to understand the safety implications of your reinforcement learning system. And given this understanding of the safety implications, we look at how we can formulate a safe control problem for different RL applications. So I will talk about a drone, about a Segway, as well as an autonomous vehicle system. And since it's kind of shielding that we apply, we will see how we can apply shielding to other problems. Also in the next lecture, how we can use shielding to even more extensive corrections of policies. And lastly, I want you to be able to analyze and evaluate safety problems in your specific RL application. So when you go into the group works and you say, I want to work on the safety part in my reinforcement learning project, that you can analyze the safety problems given your research problem and evaluate how you can solve it given the techniques we talk about today. One of the central control techniques that we will use today is reachability analysis. It's a control technique to analyze your system, also very often used in formal methods and formal analysis of systems. And the naive definition, if you not have heard of reachability analysis so far, is it computes the set of states that a system can reach over time, starting from an initial set of states. So you can imagine it as I have an initial set of states of my system. And if I apply all possible feasible trajectories to that system, to that initial states, where would I end up with given a certain amount of time? What do we require reachability analysis for? Well, for reachability analysis, we first need the model of the system to define the state space. Furthermore, we need the state transition function so that we know when we apply a trajectory to the initial set of states, where will our system end up in. We need some kind of representation of sets so that we encode what is the initial set and what are all the consecutive reachable sets along our computation. And some utility functions and operators, such as the convex hull of a set of points and so on. And I will try today to give you a glimpse overview of all of these kind of requirements for reachability analysis so that you can implement it for your own system. Let's talk about sets first, because they are the initial idea and initial object that we are dealing with in reachability analysis. So if you have not looked into the control kind of domain so far in sets, sets are well-defined distinct collections of objects. These could be discrete objects, but also continuous numbers. Usually a set can be described by enumerating all objects. For instance, this set S contains of the numbers 0, 1, 2, 3, and 4. So we have 5 elements. And you could see it, for instance, as if you have a Markov decision process in the states and you would give every state an ID. These could be the IDs of the states and you have 5 states in your Markov decision process. You can also define sets more complex by using predicates. So for instance, I can say in the set builder notation that my set S1 is defined as all element X that fulfill the predicate phi of X is true. With that, I can, for instance, say, give me all X so that X is positive, which means I have all positive real numbers, for instance. I can also concatenate such predicates to say, give me all states X so that they fulfill phi 1 and phi 2. This could be important, for instance, when you look at the case where you want to say, give me all states where the initial velocity of my autonomous vehicle is 0 and in a certain location, let's say in my parking spot. And this is the initial set of states that you consider. You can also specify domains to make it even more clear where all the element x come from. In this case, the set of all real numbers. And then our predicate function in this case is all real numbers for which they are smaller or equal to 2. And advanced notations use quantifiers. So we can say our set S is defined as all real numbers so that we can find one y in the natural numbers so that this equation holds. So we can see with the set builder notation, we can define very complex sets. And I would also recommend you when you write papers to use set builder notation. There are other ways to write sets, but the set builder notation is very common and most of the people understand it among different papers. And of course, you can also use the left side of the equation of the set builder notation for more complex notations. So for instance, it's equivalent to say all 2t plus 1 such that the variable t is element of the number set, or I can also shift it to the right side to make an equivalent statement. Then you can basically give some kind of importance, similar like in languages when you write certain things as a main sentence or as a relative sentence. Let's talk about some operations that we need for sets. First, we start with the Cartesian product. So we first have defined two sets A and B, given the set builder notation that we have defined in the previous slide. Then the Cartesian product of two sets A and B, that is denoted with the small x, is all tuples A, B, such that the element A comes from the first set A, and the element B comes from the second set B. Why is that important? For instance, let's say you have a system that where the state is contains the positions P and velocities. So how can I build the state space? I can say my state space S is all the positions that are possible times the velocities. In this case, I build my state space with the Cartesian product. Here are more examples where you can see it visualized what the effect will be. On the left side, you can see 4 sets that I defined, A, B, C, and D, and these are just one-dimensional sets along the X or Y axis. And what happens if you build the Cartesian product? So for instance, if I take set A, which are all is the line between 1 and 3 along the Y axis, and B is 1 to 3 in the X axis. With the Cartesian product, I build this small rectangle that you can see here, and it contains all the tuples as the combination of both elements of A and B. Very important, you cannot use the Cartesian product, for instance, if you have unions, and mix it up. You always need to follow the parentheses. So for instance, in this case, A Cartesian product B and the union of C Cartesian product of D is not equal to first do the union and then do the Cartesian product. Because the first one gives you the union of these two sets, the blue and the yellow, whereas the second one gives you a much larger rectangle. So this is important that you always, for these kind of operators, make sure that they are used in the right kind of order. Another operation that we need later on in reachability is the Minkowski sum. The Minkowski sum of two sets is denoted with a circle. This has a small plus. And in this case, it's defined as I take an element A from the set A and just add it with all the elements B inside the set B. If you have, for instance, vectors, you can imagine I have a vector in A and a vector B, and I just add them, and the Minkowski sum of A and B is all the vector combinations between the two sets. There's also the Minkowski difference. which is defined with minus in this case, and it's A complement plus the Minkowski sum of minus B complement. And it's very important that there are two definitions of Minkowski differences in the literature. One is for morphology and one is for coming from motion planning. And you should definitely look out for that one, that there is always a difference. So that's why I always recommend, if you use the Minkowski sum, Minkowski difference in your papers, define them through the Minkowski sum, the plus version, because then it's uniquely defined. And you will see, for instance, the morphology one is non-destructive. So you can say, if I add something to my object, I can subtract it to get my original object back, whereas in motion planning, it's not the case. Let's give you some examples. Let's say you have the set A here on the left side, which is just a rectangle, and the set B that we want to add to our set. Then we need to first define what is the origin of this set B, where the vectors start. And if I take the bottom vertex as our initial origin for the set B and add it to the set A, then it corresponds to taking this triangle and moving it along the whole object, because I added to all possible points in A. And since in this case it's a convex object, I can just take the corner points and take everything in between, because here also is the triangle and so on. And I attain this larger object. Whereas if I use the Minkowski difference, I obtain something else. And this is the small set here below. And this is, for instance, here, the version that is used in motion planning. And maybe in the first robotics class that you took, you remember that we can inflate obstacles to reduce checking the whole robotic shape, the robot shape, for collision checking to just a point. Why? If I, for instance, say my robot is this triangle, I can just check if my point B0 is within this A minus B. Because, for instance, if I'm here, I know that I'm now touching the object. Here, I'm still touching the object. But if I'm above, for instance, I'm not touching the object anymore. That's why, for instance, this definition of the Minkowski difference is used to inflate obstacles for collision checking. For instance, if you do some model predictive control, some trajectory planning, regular path planning using RRT star, yada, yada, yada. So we've talked about sets in general, so how they are defined as the set builder notation, that we use the Cartesian product as well as the Minkowski sum. But that is more the mathematic way to describe it in the paper. But how would you actually implement it? What are the kind of objects that you can instantiate that describe the set that you build with the set builder notation? Because you cannot just say in Python, this is my set builder notation, just create me the set. So we need some objects for which we can represent every element within the set. And since we are looking into the continuous domain, we need some more complex objects so that we, for instance, describe the borders around it. So for instance, if we have a rectangle, we can say this is a set and it contains all elements within the rectangle. A rectangle, for instance, is some kind of polytope, which is a set bounded by flat surfaces, by half spaces. So in this case, let me take another color. It's this side, that side, and all these sides. And we take it on the inside. So we can model the set as a convex polytope given these half spaces. And there are different possible representations. The first one is, for instance, the VREP representation, which is the ordered list of vertices of our geometric object. So for instance, if you have a rectangle, I can describe this rectangle by the ordered set of these vertices, V1, V2, V3, V4. And if I want to recreate the whole set, it is the convex hull of all the vertices in my representation. So for instance, you see here all the 4 vertices. And what the hull is doing is basically taking a rubber band around the vertices, and then it snaps around it like that. And you can represent your rectangle. This is very easy if you, for instance, want to draw something or you want to have minimal information, because in this case, I can describe the set by just 4 vertices. Another way to describe it is the H representation, also called the half space representation. And this is a bit different. In this case, we describe the set not with the vertices, but with the whole flat surfaces along all of the sides. So for instance, if I take this kind of object, then I can describe it by all the sides. 1 side, 2 sides, 3, and 4, all these half spaces. In these half spaces, when they are linear, we can just use this linear combination given the notation of A, X smaller equals B, which you can see in this notation. And if I form that then into a matrix, then I can describe my whole polytope P as all X, for which my half space constraints H times X smaller equals B is satisfied, which is really, really cool. If you already see at this kind of definition, it's similar to what I showed you in the set builder notation. It's this phi. And it's very, very nice if you want to check, is a point, a state in my set? Because if you evaluate this one, it is smaller equals B if it's inside the set, so smaller equals B. Whereas if it's outside, it is greater B. So you can see with that kind of notation, it's much harder to interpret how does the object look like in the end. But for instance, if we want to test some inclusion, if is my state inside my set, that's much easier because we can just compute this linear equation, does it hold or not, and then we know on which side it is. Whereas the first representation is much easier for drawing, for interpreting, and so on. I already mentioned that these representations have some pros, depending on what kind of operations you want to do, and of course some cons. So for instance, the VREP is often has a large number of vertices if it's a complex polytope, because I need to describe all the possible vertices, whereas the H representation makes it much more difficult to visualize it, because the half spaces are more difficult to evaluate, and also some operations are not straightforward. For instance, if you remember the Minkowski sum, I told you if it's a convex object, I can just take, for instance, the small triangle that we had around my vertices. So I have just 4 times, and then I compute the convex hull around it, and then I have my A plus B. Whereas for half spaces, it's not so straightforward. Here you can see that for a given polytope, the same polytope did both kind of representations. On the left, you see the vertex representation, where we have 6 vertices that describe the polygon from V1, V2 to V6. And on the other side, we have 6 half spaces where the normal is pointing outwards of the object. These 6 half spaces, of course, extend into the infinite. And with these 6 half spaces, I can describe the same polytope that you can see here. An example, for instance, here on the left, that you can see that this is the same polytope that I showed you here with the vertex representation. You see it's just the enumeration of all the vertices. And on the right side, that's the representation you get when you compute your half spaces. So you get the matrix as well as the B to check if it's valid or not. So remember, it's H times X smaller equals than B. If you want to try out for yourself how it works, you can use this kind of example for yourself at home, where I have these 2 sets X0 and X1 defined. And you can try to find the V representation as well as the H representations for both the sets X0 and X1. For instance, for X0, if you want the half spaces, that's more easier because they are just parallel to the X and Y axis. For the X1 set, it's more difficult because we have a linear one that is in between X and Y. Good. Before we go into a small break so that you can recover, I try to usually use more breaks in between. I want to talk about the last representation so far is the zonotope representation. The zonotope is a very special object, especially for reachability analysis, and it is defined as the Minkowski sum of line segments to form a polytope, and it's called a zonotope. The mathematical definition is seen here below, where the zonotope is defined with the center that defines the center of the polytope, and D generators GI. And these generators are these line segments that we add with the Minkowski sum in order to compute it. So you can see that they are all axes so that I start from my center of the object and I find some linear combination of the generators so that it is inside the line segment. How does it look like? I think that's often more easy to understand when you see an example. For instance, if I look at the zonotope that is defined below, here I have 4 line segments. And how it's done is you have the center P, and we take the first line segment. The first line is this direction. And what I do is I use the Minkowski sum to add it. So you see I have the line in one direction added, and I add the same line, because it's the interval from -1 to 1, negatively. That's why it's symmetric to the center. If I have those two, remember this was the line before, I add another one that's L2. So I add here a side, there a side, and then I get the rectangle. If I add another L3, another generator, I can add the generator as well. So you see that with L3, I obtain my the previous zonotope by adding L3 to the representation. In this case, you see, can add, let me take another color in this case. So L3 is red. I can go to each side to add my L3 and I get the next object. And with that, you can generate more complex shapes for the kind of sets. The cool thing with that one is it's really easy to define. It's just the generators. You have the Minkowski sum, and they are symmetric. And you will see later on that in the reachability analysis computation, we will use a lot of Minkowski sums. And the Minkowski sum for these kind of objects is very easy to compute because it just add the generators from this from the operation and have more generators. So it's very easy to compute the Minkowski sum without actually doing the convex hull and so on. So far we talked about the sets, how we can build them mathematically and how we can, for instance, define a polytope or a zonotope in order to find a way to actually program it into a computer. The next ingredient that we need is the dynamical system, where we apply the sets and reachability analysis onto. If you remember from the lecture of Hang, the dynamical system is defined by a set of feasible states X, which describes all the possible states that the system can have over time, as well as we have a set of feasible inputs U. These are all the inputs that I can apply to the set, to the dynamical system, in this case, defined by the set U. And then in general, you can define the dynamics of this. Say we use disturbance-free systems by a differential equation, x dot over time. And it's often written in this way, that we have a function that is depending on the state at a given time and the input that we apply to the system. And this kind of differential equation we will use in reachability analysis, but certain simplifications. So for instance, that the system is linear, but you can also use nonlinear systems for reachability analysis. Moreover, we assume that we have a given initial state. So for instance, for the dynamical system, it's often that you say my x0 is the initial state at a given initial time t0. The cool thing is we can also now define it differently by saying our x0 is in a set of initial states, because let's say you have a drone and you cannot perfectly localize the drone. So instead of having the drone at a certain position, we can draw, for instance, a circle around it, because that's the position uncertainty we have. And with that, we can describe the uncertainty in our system as well. An input trajectory is a series of inputs over time that we apply to our system. And we denote it here as the input u that is applied from the time interval t0 to th, where all the small u's in between this time interval come from our set of feasible inputs. And later on, we will use the operator he to describe that we evaluate the system given one initial state that we start in. So let's say that's x0, and apply the trajectory u. We want to know where is the system at time t. It's basically a simulation of the trajectory. So if I take my trajectory here in blue, it is from t0 to th where the system is. And I want to query my system, for instance, at this time t, where is the state in this case. So it's xt given my trajectory. A system is linear if the superposition principle holds. So basically we can say if it is linear, if I apply a function x1 plus x2, I can also do it by saying first I apply the function to x, then I add the function of x2 on top. And as well, I need to do the f of a times x equals that I can take out the a and multiply this constant factor a before our f, after our f function is applied. This is important because the linear systems is usually much easier to handle with. Sometimes it's not possible to get the linear system directly out of the way, but what we can do is, for instance, linearize the system or use much higher operators. So for instance, the Koopman operator and so on, where you get such high dimensionality that you try to make it seem linear. And the general state representation of such linear system is very cool, because what we can exploit is that we can separate our transition system into two matrices, the A matrix, let me go back to my pen, and the B matrix, which is basically describing the dynamics just of the state itself and what happens to the dynamics when I apply an input. So for instance, if you have an autonomous vehicle that is driving in this direction and with a constant velocity of, let's say, 30 kilometers per hour, the A matrix, if we don't apply any control input and keep the velocity, would just define how the position is changing over time. And if I would use the brake pedal, it would describe with the B matrix how my velocity is reduced over time. That's the continuous time version that you see here in the first line. And the second line is describing the discrete time version, where instead of having a time factor that is continuous t, where here the t is element of our real numbers, it's just discrete time steps k, for instance, 0 to some end horizon n. So we have the necessary ingredients to now go further and look at reachable sets. I told you in the beginning, the naive definition is the reachable set describes all the set that the system can reach over time, given an initial set of states and the possible trajectories in this case. So let's define that in a mathematical framework, given what we've learned so far. An initial set of states, this he operator, and so on. So the forward reachable set RF is the set of states that the system can reach at a given time t, when we start from the initial set of states x0 and considering all possible inputs u. Which means I evaluate my system at the time t that I want my reachable set to be computed for, given an initial state and all possible trajectories, which we here denote with U and the dot. If we have an initial set of states, you see, this is how we use the set builder notation to actually specify that we have some uncertainty. So everything on the left side must hold for all the possible initial states x0 in my initial set, which you can see here, for example, below. And I simulate the set for all the times until my query time t, given my evaluation function, so that the resulting state is still a feasible state, because sometimes you can generate states that, for instance, are, let's say, in collision or something that you don't want. Then you still make sure that you always have admissible states, and you define that all the inputs must be feasible. We can also define a reachable set for a time interval, which is basically the union of all the reachable sets along the time. A lot of math again, let's visualize it. Here we have the initial set x0, and we just pick one initial state, x0, from this initial state, and one possible trajectory that you see here in orange. And then we obtain this final state, xt, given this trajectory. Reachability analysis is a very handy tool because it not just looks at one possible trajectory, but at a lot of trajectories. Here in this case, 5, but what we do is for all possible trajectories. So the cool thing is, reachability analysis computes us the set, that's the forward reachable set at time t. It's basically all the possible trajectories that come from the initial set x0 and end up in our final set Rf of t. And if I computed the reachable set for a time interval, I get this tube around it. So you see all intermediate states. So why is that important? The cool thing with the forward reachable set is, what we will see later, we can check, given my initial states and the possible trajectories, will I reach certain things? In the beginning, I talked about this autonomous vehicle example, where we, for instance, might want to ask, can the autonomous vehicle reach its goal? Let's say the goal is some set here, and we see that the reachable set intersects the goal set. We can definitely tell that the system can reach the goal with some trajectories. And we can do this as well for unsafe stuff that we say. If you remember what Alexei was also saying in the specifications, we want to sometimes reach certain things or avoid certain things. And this reach avoid is now translated into the continuous domain with reachable sets. We will see that more later when we construct actually the safety layers. So the purpose of the reachable set for our lecture today is to say, is the system able to reach certain states, or is the system not able to reach certain, in this case, unsafe states? So how is this done? One important note for that is, in general, we cannot compute exact forward and backward reachable sets. Let me talk about that. Backward reachable set, we will look into it a bit later, but it holds for both the forward and the backward reachable sets. Since we do some operations, and these operations have certain errors, we will not be able to compute the exact reachable set. It's only for a certain class of systems, for instance, nilpotent systems and so on, there we can compute exact reachable sets. It's, for instance, due to Taylor approximation and so on. Instead, we are interested in over or under approximating these sets. Over means that if we have our set, it's larger than the actual set, and under approximation means it's smaller than our actual reachable set. And to be really, really cool, we want to have a tight approximation, because otherwise we could say any reachable set can be approximated, over approximated, by just saying the next set is the whole state space. It doesn't make sense in this case, because you always say it can reach everything. It's a valid over approximation, but we usually want to have it as tight as possible so that we are not conservative. We will denote the over approximation with this over bar. And we obtain such over approximations either by using an over approximative model, meaning, for instance, I can use a dynamics model that is capable of doing more than the actual system, or by over approximating the reachable set computations in between. And the same is for the under approximation. However, I need to tell you here that obtaining over approximations is usually more easy than under approximations. Here you can see how we can use that in order to ask, is our system unsafe? So we have an unsafe set of states F, forbidden, and our initial set of states X0. How can we now determine, is our system able to reach the unsafe state? Basically, we use reachable sets. First, we compute the reachable set. That's in this case, the exact reachable set, for instance, and you can see it's not touching our forbidden states. So what we could say in this case is this reachable set is not reaching the forbidden states, so the system is safe. However, what we want to do is, in this case, use over approximations. So for instance, if we use the over approximative reachable set, because let's say the current set that I show you now is just any approximation, we want a tight over approximation. We want to guarantee that we cover all trajectories. That is the over approximation. So for instance, you see that these two trajectories that I denote here at top and bottom, if we don't use a tight or a proven over approximation, we might have forgotten some trajectories in the computation, which might lead the system to still reach this unsafe state. If we use the over approximation, which is guaranteed to cover all trajectories, we get a larger set, as I said before, but we can definitely answer our question. Given our over approximation, which you can see here in this light turquoise kind of color, you see that given the over approximative reachable set, our system is definitely able to reach the unsafe set. However, given the tightness, it could be that, yes, it is too large, the set, and we think it can reach it, or it's not. So that's the importance why we want to have tight over approximations, because it can also give you that over approximative set, which is much larger, but all the time reaching the unsafe states. So that's why we want to have a tight over approximation of such sets. The cool thing is now, first we answered, is the system able to reach the unsafe states? And given our over approximative set, we can say, yes, it is possible, but we are not knowing for sure. The second question we can answer, given under approximative reachable sets, is, can we still find a trajectory that is safe? The under approximative reachable set is smaller than the actual reachable set. In this case, the original set that I drew here is now our under approximation. And you see that the under approximation is not touching the unsafe states. So we can say, yes, there is the possibility, given the over approximative set, that we reach the unsafe states, but there are motions that are still collision-free given our initial set. Here's a question. So the question is the tightness about finding an efficient trajectory to the safe set? Since I said that we are guaranteed to get there if we make the over approximation really big. So the guaranteed is only about the guarantees that the over approximation gives. So the over approximation guarantees that we did not forget any trajectory that is still possible to be executed. And if the over approximation is touching our unsafe set, we can likely say that there is a possibility for the system to become unsafe, but it's not sure, because it's just assuming there are trajectories that bring you to the forbidden set, but not all, which we show with the under approximation. I hope this answers your question. So the tightness is not about finding an efficient trajectory to the safe set, but is there one trajectory, most likely, that brings you to the unsafe set? Or with the under approximation, is there a trajectory that is not bringing you to the unsafe set? So it's more kind of binary answer of yes or no. And you will see later on, that's the second question from the safety filter that I posed you in the beginning. If I have this kind of system and always this over approximation, it will say, yeah, the system might become unsafe. But what do I do now? What kind of trajectory do I execute? And this is what we will see later, because now it's just about, yes, it will reach unsafe state, or no, it's fine. In order to compute the forward reachable set for linear systems, there are different approaches that you can use. For instance, the Hamilton-Jacobi reachability, where you solve some Hamilton-Jacobi equations, or a propagation-based version, which I want to explain to you today. For that, let's just consider a discrete time horizon that we split into k equal time intervals with a step size delta t. So let's say if we have this time horizon from 0 to k, we just put it into equally distant small intervals. And the propagation-based version works by computing the reachable set for the first step, take that result to propagate it to the next step, to the next step. So basically what we are doing is we exploit also the superposition of the system by obtaining the reachable set as the homogeneous solution plus the particular solution we given the Minkowski sum. We will look at this in the next slide a bit more visually. But then the cool thing is what we can do with this propagation-based version, we can compute the reachable set for our time interval by just taking the union of computing the reachable sets for these small propagations. And as I said, important again, in general, we cannot obtain exact reachable sets. So how does it look like when we want to compute the forward reachable set for a linear system? So first, we compute the representation of the initial set, which means we use, for instance, polytopes or zonotopes to cover all the initial states that we want to have, for instance, given our measurement uncertainties. Then we propagate the homogeneous solution H of our linear system, which is basically in this case, because the convex object, given the solutions of our system, how is it moving over time, given the current dynamics in the set. And what I do is I obtain this new set here. What I then need to do is I compute the convex hull between our initial set and our homogeneous solution. Why the convex set? The convex hull in this case, because we compute everything for time interval from, let's say, t0 to t0 plus delta t. So you want to cover everything in between. So when we have that, what is missing is the particular solution. In order to add the particular solution, we need to first add an error term E to our convex hull. And this error term E is just to cover for certain trajectories that are bent. And you can compute the error term. There are certain ways to compute the error term so that you can always have, the, for instance, over approximation and add it to your system. And then we come up with the particular solution, which is our input. And we take our input set, this is in this case the P, and also add it to the convex hull. So you see from all the sets, we compute the reachable sets given the convex hull operation, the Minkowski sum. So the computed reachable set is our convex hull plus the error term plus the particular solution, and this gives us our reachable set. So with that, we just described how we get from one time interval. So what I can do now is, if you remember, I start for my whole time horizon and I split it into equal intervals. I apply the same operation to get from one interval to the next. And then I use the result that I have as the new initial set, propagate it again, have a new initial set, propagate it again. And with that, I just go through a for loop of the same operations until I reach my final discrete time horizon k. So the notes here are that we use the resulting RF for each of these time steps or time intervals for the next propagation step. It is very important that you need to check if the input set, that's the P here, input set contains the origin. Why is that important? If you remember from our initial Minkowski sum slide, where I had this B of 0, we need to have defined the origin so that it fits here, because if our original of our P set is not containing the origin, there is some hole in between. We don't want that. So you need to check if the input is there. If it's not, there are certain ways to account for that by doing some transformations. Sonotopes, as I said, well-performing set representation for reachability analysis. Why? We have so many Minkowski sums here. Perfect for that. We just add the generators. Boom, done. Only drawback is, in the end, you might have a lot of generators, making your sonotope really, really large, and you need to store a lot of stuff. So what you usually do at certain time steps or for certain complex systems, you reduce the order of the sonotopes, and the order is the number of generators you have. So for instance, if I have this kind of sonotope here, let's say it's a sonotope, the order reduction technique is I cover it with a simpler object that covers it, but has less generators. And with that, you can get less overhead by using less generators. But of course, you can see, and that's the problem, you cover some space that was not originally in your computation, which is also the so-called wrapping effect, that you cover in your simpler representation or certain operations volume in the set that was not originally there. Just to note that. And then you can get these really cool images, for instance, with the propagation set, where you start here with, for instance, your initial states, initial set of states x0. And you see that I plot the sets, it's taken from GR, that I take the initial set and then propagate it for all the time steps. And then you get this nice reachable set tubes. That's why they're also often called tubes. Looks really nice. Some people would even consider it art. It's really cool. And this is what we can use in order to see what kind of states is the system able to reach. And as I said in the beginning, if I, for instance, have in this part here an unsafe set F, we can see that our system on the left side would be able to reach the unsafe set F. But if I put it here, the other system is not able to reach the unsafe set F. So we can say no matter what kind of trajectory we execute, there's no chance for the right system that we will reach an unsafe state. So this one is proven, because we can now give you a mathematical proof. And that's why in SafeRL, the formal methods and formal control community is very strong. We can give you a proof that given the initial set of states, and let's say the policy gives you all the possible trajectories that you can execute, or policy pi, we will not be able to reach an unsafe state. Whereas on the left side, if we take our policy, there might be executions or rollouts of our policy that reach the unsafe states. Yes, there's a question. Damianos, you have raised your hand. Now I can hear you. No, I cannot hear you anymore. If your microphone is not working, you can also post your question in the chat. Otherwise, if you have the question, I will go back to it in the chat, but let's continue so far in the matter of time and the interest of time. There are different toolboxes that you can use already in order to compute reachable sets. You don't need to implement all the kind of mathematical operations. So for instance, there's the Cora toolbox for MATLAB that is developed at TUM. There's a Julia version of it, Julia Reach. And there is also Flow Star and also SpaceX that you can use to compute reachable sets. And now I see the question. So he wanted to ask about how this works when the system is uncertain, for instance, additive or multiplicative uncertainty. I use the system that is disturbance-free, but if you have some disturbances, it's another convex set that you add, for instance, because you might say, I add a trajectory given my particular solution, and I enlarge those again, depending on what kind of uncertainty I have, if it's additive uncertainty or multiplicative uncertainty, as you said in your question. But there are different ways to integrate that as well by just enlarging the sets again. Hope this answers your question. So another one. So you're restricted, that's the question, to convex polytopic uncertainties only. No, you can compute a reachable set for also non-convex and polytopic uncertainties and so on, but it makes it much more complex. Because then sometimes for these non-convex shapes, you get wrong approximations or you miss solutions. That's why usually we try to use some linear system, or we use convex operations not in order to not get undesired system behavior. But for instance, for nonlinear systems or for non-convex sets, we can also apply these methods, but then you need to be much more careful how you can apply it. For instance, if you look here at the third toolbox, flow star, they specifically also consider nonlinear hybrid systems where you even have switches in between. And the current literature and research in reachability analysis is heavily focusing on how can we use reachability analysis for nonlinear systems, as well as for non-convex things, for uncertainty disturbances, for hybrid systems, and so on. Thank you for the question. These are the two boxes that are out there. There are much more that are now developed. So if you are interested in getting to know also, for instance, some examples, all of these toolboxes provide you some examples already. You can just click and execute and use for yourself. Good. In the last kind of 18 minutes of our lecture today, I would like to talk about how we can use the information about reachable sets in order to bring it into our RL system and this specific safety filter that we talked about in the beginning. So we already saw what reachability analysis we can answer: is our system able to reach certain unsafe sets or not? And we can use that kind of information in order to build a safety filter. So how does it work? So we have an initial set of states x0 from our system and a forbidden set f. With our over-approximative reachable set, we can say there are unsafe trajectories that our system can use in order to reach the unsafe set of states. So the system is potentially unsafe. It is not guaranteed because we use an over-approximation. So there might be that it's not the case, but in order to be sure, we can in this case say there is a chance that there are unsafe trajectories. The under-approximative reachable set in this case would say there are still safe trajectories that the system can execute. If this set also collides all the time with the forbidden set, then we know the system is doomed and it will probably collide, something like that. But in this case, here you can see there are still some safe trajectories. So for instance, there's this kind of trajectory that we can take, and this trajectory in orange that you see here is not colliding with the unsafe state, so we can take that. And the fact that we can exploit now is, for the over-approximative reachable set, we assumed we can execute all possible trajectories. But usually we have a policy given, trained by our reinforcement learning agent, and this policy gives us a distribution of trajectories that the system can take. So it's not all possible trajectories, but usually much smaller. So what we can do is we can only compute the reachable set either along a given trajectory, or what you can also do, you can try to compute the reachable set along a policy. So you have a policy of trajectories that the system might execute, and we compute what the system can reach given this policy, and also uncertainty. So for instance, here in this case, you can see we have only one trajectory, but I can still compute a reachable tube around it, considering that my system might sometimes deviate because I have some uncertainties and my system might deviate. And with this tube, I can also say, given this current trajectory or my policy, the system, even by deviating from the policy, because of some unmodeled uncertainties that have not been yet learned and accounted for in the policy, our system is still safe because it's not reaching unsafe states. What I can also use reachability analysis for is to compute how unsafe states will move in the future, because in the previous slide you saw this set was more or less static. So we assume that's, let's say, a wall. And this system could be a drone. And we see, is the drone able to hit the wall or not? But what if this one is not static anymore, but it's, for instance, a human that is walking around the workspace of the drone? How can we predict how the human, what kind of positions the human can reach over time? And we can also use reachability analysis for that. So we use it for our system, and we use it also for the unsafe states. So for instance, here, if this was the initial set where the human was detected given cameras, we can also predict, given the model of the human, where can this human go along? And with that, we can check, is our current policy safe given the motion of the human or not? I want to first talk about an example for autonomous vehicles where we use both kind of techniques. You can see the autonomous vehicle here in blue and all other vehicles for on a highway in black. In this example, we use a continuous state space, but a discrete action space. So to make it a bit simpler. So in this case, the autonomous vehicle, the agent, can perform a lane change to the left lane or to the right lane, or it can continue on its lane. The goal in the reward function that is encoded is to maximize the velocity on a 3-lane highway. What we want to use reachable sets for is to first predict the future positions of surrounding vehicles. So to predict what are the other vehicles able to do. This is interesting, for instance, if I do this lane change to the left lane, is the vehicle behind on the left adjacent lane able to reach me when it's accelerating, so that the agent is potentially causing a collision? And I can use also reachability analysis to account for uncertainties while executing my trajectory. And with that, we can define some kind of free space. This is a figure taken from the paper, so don't be confused. This F in this case is not unsafe, it's the free space F. So what we want to check for our safety filter is our agent at all times along the execution of the policy within the free space that is guaranteed to be safe given our reachable set. And then we can say an action is safe if the agent is always within the free space FT. And that's the trick that is used by the authors in this paper in order to learn if the current lane change will potentially be unsafe or not. Let's look at the video.
In this paper, we propose a reinforcement learning frame.
Turn off the audio. Here you can see the reinforcement learning agent driving in this 3-lane highway, and it's just performing some actions in order to learn the policy. So in this case, it changed to the left lane, it's driving and driving. However, sometimes during the random exploration, it might, for instance, execute some lane changes that are not safe, which we'll see now, for instance. Now it wants to just turn left, and it collided because it was not yet accounted for. And this is the problem in reinforcement learning. This one, a double lane change, crashing into another vehicle. If we use the safety verification technique, we can ensure that the action that the vehicle wants to perform is safe or not. And then in this case, you see that we are able to perform the desired task while guaranteeing safety at all times. You see the agent here called remote TRM is always trying to go to the left lane if possible. And if there's a vehicle, changes early, because it's not possible to change to another lane if the safety filter says no. So the safety filter in this case checks if the agent wants to go to the left adjacent lane. And if it's unsafe, it says you cannot take that action, take another action. Then the policy might say, okay, then I take the as the second most high rewarding action, the right lane change, if this is unsafe, also. But the cool thing is staying on the lane action will always be safe. That's why in this case, we always have a safe alternative plan. This brings me to this question again, where you see here. We can check if the action, for instance, the lane change, will lead us to an unsafe situation in which our executed trajectory might collide with an unsafe set F. But then we don't execute this action, but we need to execute some other action, especially if it's a vehicle driving on a highway. What can we do? In this case, I told you the authors exploited that the stay on the lane, don't do a lane change action is always safe. So you always have some kind of backup plan that you can execute, for instance, to stay on your lane. Let's say it's denoted here with this tube that is not colliding because you stay behind your preceding vehicle. The question that arises now is, and that I want to talk today in the last remaining minutes that we have, and next week, how can we synthesize motions that are safe at all times? Meaning, if the answer to our safety question is no all the time, how do we make sure that there's at least one motion that is safe at all times? So how can we make sure that the policy always has a safe backup plan that it can execute to not collide with a wall, with a human, and so on? And I want to give you a small motivating example where we used so-called fail-safe trajectories to plan provably safe motions for an autonomous vehicle. In this case, it's classical motion planning, but you can apply this same technique also to our reinforcement learning. And let me give you the high-level idea of what fail-safe planning / control is doing. You can see that we have an ego vehicle that is driving along the lane of a T-junction, and there are certain other traffic participants. The ego vehicle is planning an intended trajectory that it wants to drive along, but we don't know if this intended trajectory is safe, since the other traffic participants might be able to execute different legal behaviors. For instance, it can turn left, this vehicle, or can turn right. And depending on what the other traffic participants do, this intended trajectory might become unsafe. So for instance, let's say if the rightmost vehicle is turning left or right, there is a chance that our ego vehicle along the black intended trajectory might collide with these vehicles. So what we've learned so far in this lecture is we could use reachability analysis to predict the unsafe sets. In this case, all the blue regions that you see here are our unsafe sets projected to the position domain. So you can see where the vehicles could be located over time. And with our safety filter, we could now say there is the chance along this intended trajectory in black that we collide with the unsafe set F because they're intersecting. What fail-safe planning is doing is we try to compute a backup plan which keeps us safe by avoiding these unsafe sets. So for instance, let's say the pedestrian is stepping onto the road. What we can do is we can compute a backup plan, this is this red plan, that branches off our intended policy and just avoids this kind of unsafe set. So you can see it as some kind of backup plan that we have in mind in case something unforeseen happens, or if our action or trajectory that the system wants to execute is unsafe. In our lane change example that I showed you before, it was a simpler situation. In this case, if our lane change left or right is unsafe, the red trajectory is always stay on your lane and follow the vehicle in front of you. But for more complex systems, let's say you have a robot manipulator, it could be that we stop the robot before the human arm, let's say the human is able to reach that manipulator arm. And these kind of things you can use in order to have a safe backup plan all the time for your reinforcement learning agent. Same for a drone. We will see that later for a helicopter example, an autonomous helicopter. How can we, for instance, find for such a high dynamical system always a backup trajectory? So if there's a wall or human, the drone can, for instance, immediately come to a stop and just hover. An important feature here is that all the time we need to keep the system in a set of safe states, and we will talk about this, how to compute these set of safe states in the next week, where we use some control invariance techniques in order to derive sets of safe states for our system so that we can check, is our reinforcement learning agent always in the set of safe states? And when it's about to leave the set, we can compute a phase-safe trajectory that keeps you in the set. Some preliminaries again for that is state space X is still the same. Input trajectory, input space still the same. Now what we have on top is a state trajectory that we also consider, which is basically directly the trajectory of all the states that we have, just for simplifications. We have a workspace or environment for our reinforcement learning agents that is, in this case, we consider collision-free motions, is occupied with obstacles B. We can obtain the obstacle footprint over time as occupancy sets. So in this case, what I showed you previously in the slide with autonomous vehicle, these blue sets, we can, for instance, describe where these obstacles are in the workspace. So we do the collision check in the position domain by obtaining the occupancy sets. So for instance, if we have a human, the occupancy set might, for instance, be the circle where the human is standing. And if the human is moving over time, we always obtain as the occupancy the circle around where the human is walking. If we take the time interval, we have again such a tube. The set of collision-free states, that is a very important part that we want to consider, are all states X, so that our occupancy, meaning this operator here, denotes the dimensions of the drone, for instance, the dimensions of the vehicle, the agent in this case. Are the dimensions of the agent not intersecting with the occupancy of our obstacles? Here there is missing a 0 set. So is it always empty? That's the important part. Meaning we never collide with any obstacles. These states are the collision-free states. For instance, in this example here, go back, the ego vehicle, you can see the intended trajectory. This is our OB of the obstacle 1, OB of obstacle 2, and our collision-free states given our ego vehicle shape would be, for instance, everything where the vehicle is not intersecting with any of the obstacles. And here I projected to the position domain already, so you see which positions are collision-free positions. And this is what we will use later on to compute a set so that this, for instance, ego vehicle is always within the red zone here, that it's not colliding with any obstacle in our environment. A very important fact for that is persistent feasibility. Persistent feasibility means that given an infinite time horizon, our system can still be safe. Because the problem is, even for, and also in reinforcement learning systems, we always execute given one time step or a limited prediction horizon. So you see, if we have both trajectories, let's say these are the policies, and this is the end position of the vehicle, so the front bumper, both of these trajectories x1 and x2 are safe, both. However, if I consider the velocity is definitely much higher than 0, so we are not standing, there is a difference between trajectories. Whereas if this vehicle is here, and we then need to execute the next policy or get the next action from the policy, this one will cause a collision because we have a velocity, we cannot brake in time anymore, and the vehicle will crash into the roadworks. Whereas the second trajectory is still fine because there's nothing coming afterwards, so we can still find a collision-free motion. So the definition of persistent feasibility is extending collision-free trajectories by saying we can define if a trajectory, or we can determine if a trajectory remains collision-free when we perform a replanning or execution of another action from our reinforcement learning policy. This brings us to safe sets and invariant sets, how we can obtain a set of states where we can always remain and find a new collision-free trajectory, this invariant sets. And this is what I want to talk about next week, where we answer the second question of our initial slide. If you remember from the safety filter, we first determine, is this action possibly leading to some unsafe states? Yes, we can determine that now with reachability analysis. The second question is, what do we do if we have an unsafe action? How can we find some safe action? This is by synthesizing backup plans, or alternative plans that the reinforcement learning agent can use, for instance, during exploration or during execution when we have already deployed the policy, to keep the system safe, which we already saw, for instance, for the vehicle with the lane changes. And next week, we will go in more details into the theory, how to compute it, and we will look how we can do that for an autonomous helicopter, for Segway, or for a drone that is using reinforcement learning agent in order to learn a controller to fly very nicely. But this brings me to the end of my slide of my part of the lecture today. We have covered the 90 minutes, and I will upload everything again on our social page. If there are questions to the content we had so far, let me know, write me an email. And don't forget, next week we are talking about the group forming, and probably also the week after. But other than that, I thank you so much for staying here with me today, for listening, for all your great questions. And I will stay some more minutes in case you have questions. Other than that, I wish you a great rest of the week, a great Easter time. Take care of yourself and find some nice Easter eggs for yourself, and see you next week. Bye-bye.